Hello, welcome back to CS 700, Computer Science of Continuous Data, Algorithmic Foundations of Numerics. And today we're going to start discussing reduction between continuous problems. As you know, the famous complexity class NP is defined as the hardest problems in NP with respect to polynomial time reduction among decision problems. But decision problems only make sense in the discrete setting because in the continuous realm, in the realm of real numbers, any discontinuous function is uncomputable anyway. So in order to translate the notions of complexity and in particular the notion of polynomial time reduction to the discrete, to the continuous setting, we need to make some amendments, and the tools will be provided in today's lecture. So let me start the slides here. And here we are. Right, so reduction between continuous problems. And yes, we're going to start talking about computing integer functionals and integer operators, that is a higher type computation. And then we'll recall various types of polynomials used to bound the computational costs, resources, such as running time or memory. And then we'll recap various degrees, notion of degrees of such polynomials. And in particular, we will introduce second order polynomials and discuss the degree of second order polynomials and its properties. So let's start right away. Computing integer functionals and operators. And to recap, we've implicitly already discussed that in a static setting when we discussed polynomial time Turing reduction between integer function problems, namely integer functions A and integer functions B. A is polynomial time Turing reducible if A can be computed using B as an oracle in polynomial time. So here's the formal definitions. A and B are not decision problems, but slightly more general, still discrete, but function problems. And we write A is Turing reducible to B in polynomial time if the value of A of an argument X can be expressed as the value of B after some initial transformation of the argument X, which is an integer or tuple of integer. And then there's another transformation of the value returned by the oracle call to B, which can use the resulting value and can use also the original argument X. So G is a two-variate function and F is a univariate function. F is the initial translation to the argument, which is then presented to B, and the return value of B can in turn be transformed using the function g. And for polynomial time reduction, these functions must be polynomial time computable. And here's the associated picture. So there's an integer input x, and we want to calculate a of x, the value of this integer function a on input x. And now, as opposed to or generalizing ordinary computation, we can now make use of the additional integer function b in order to compute a in the following way. First, we process the integer argument x according to the translation f to obtain a new integer y. And this integer y is then fed into the function b, technically in terms of an available, in terms of an oracle, so making an oracle query of b to b with value oracle query y. and then take the return value of b, which we here abbreviate with z, and apply another transformation to this z, which is here to call g, which gets to can make use of the return value z and can make use of the original argument x. So g is a function which receives two arguments to produce the return value and to produce the actual desired value a of x. Okay. Now that's a classical polynomial time Turing reduction with only one query that's indicated here with a square bracket in red. The one means only one query can be made. And more generally, if several queries can be made, so here's a way of writing this more concisely. So this is now a is in this way expressed as the composition of three functions where the oracle b is kind of wedged in between the initial translation and the post-query translation. And so this is a particular kind of, if you let b vary, then this gives various kinds of functions a. So this is a particular kind of an operator that turns b into the new function a of b, and as b varies here, we get various functions a, and the mapping from b to a, that's an operator. In this case, a very special kind of operator of this kind of composition product form: first translate, then invoke b, then translate again. And more generally, if we allow more than just one query, like in this example, that means that the result of the first query can further be processed further and can be used to produce another query, which we here call y prime, can be used to make another query to b, give another answer, and so on. But this process can be repeated many times, but each time the oracle gets invoked is of course also charged to the overall running time of this translation, and the overall running time must be polynomial. And so the general setting is that we have an operator which is polynomial time computable, which maps the oracle b, the given, now it's given, it's not fixed anymore, the given oracle b as a function to a new function a. So the difference to our previous setting is that previously b was fixed, and now we let b vary to obtain some kind of higher type computation that maps integer functions b to the new function a independence on b. And now let's have a look at the computational cost of this translation, including the cost of making the oracle calls. So, but first let us query the operator. So here the result of the operator is a function a, which depends on b. And we now query that to convert it into a function null. Namely, we evaluate the resulting function at a given integer argument x. And so now we consider two dependencies: the dependency on b, the oracle function, and the dependence on x, which is an integer or integer tuple. And the result now is not a function, but now just an integer or an integer tuple. So it's now we have converted this using currying the operator converted into functional. And the cost of this functional, the running time, of course, will as usual depend on the natural number argument x. We already know that. More precisely, we consider the dependence on the length of x when given in binary. Remember, L of x is roughly the logarithm of x up to some rounding. That's a binary length. But this functional, being of higher type, now in addition depends also on which function b is given as argument, right? So b is a function which is given as argument, and being given as argument, that's the essence of higher type computation of codimension functionals. And different function arguments B will also result in different running times, as you can imagine here. The running time it may depend on B in several ways. For example, for a different B, there could be more iterations than for another B, but also the different B could return larger or shorter queries, shorter answers to the same query by prime. So that's various ways in which the changing the Oracle B function can affect the running time. And of course, we need to take that into account when we want to talk about polynomial running time for this higher type computation for functionals. And what we consider here is again the dependence on the binary length of this function now. But this is a function, not a single object, so its binary length is not just a single number as the binary length of a natural number, but instead the binary length here is in turn a function which we're going to abbreviate with lambda of b. So L, small l of integer x is a natural number, is a constant, and capital L or lambda of the function b is a function from natural numbers to natural numbers, which takes the length of the argument to b and returns the length of the value b of x. Okay, and we want to be able to talk about such running times. What does it mean for such a computation to be a polynomial time computation when the running time depends not only on the binary length of the input, but also depends on an integer function as a higher type object. And this is exactly the topic of the next slide, where we review and generalize various polynomial resource bounds. So the first resource bound are our standard univariate polynomials over natural numbers, right? It's no loss of generality to consider only natural number arguments. Real number arguments can be rounded to the next larger integer natural number, and negative integer arguments can be dropped anyway. So univariate polynomials over natural number coefficients in one variable n, which will then later be used to represent the binary length of the input. That's what we call polynomial running time, complexity class P, complexity class FP, and polynomial memory bound complexity class P space. And one way of defining the set of univariate polynomials in one variable over natural numbers is to look at it as the smallest least set of terms here being meaning formal expressions, the least set of terms which include the constants 0 and 1. These are the constants that comprise the natural numbers as a structure in the sense of model theory, and one initial basic or atomic term, namely the variable n, that is essential to the polynomials, right? So all polynomials in the string share the same variable n, and so these are definitely polynomials. And now we can use and combine them to construct larger polynomials. Namely, we take the closure of these atomic terms under addition and under commutative multiplication. This yields the least set of terms which contains these and is closed under these two arithmetic operations is the set of univariate polynomials over the ring over natural numbers, right? And easy but important observation is that this set of terms is closed under composition in the usual sense, which is not axiomatically imposed, but it's a consequence, right? So if we have closure under multiplication and addition, then we also get closure under composition. That's univariate polynomials or standard polynomials for resource bounds because each such polynomial gives rise to a function from natural numbers to natural numbers, right? So here these are just formal expressions, these are terms, but we can interpret any such term as a function from natural numbers to natural numbers if we interpret the variable, if we uh, make an assignment of the variable to some natural number, then the polynomial induces a mapping from natural numbers to natural number, which we here by gentleman abuse of notation also denote by p. Right? So from natural numbers to natural numbers, polynomial as a mapping. That's an interpretation. And indeed, we can I actually identify that because the natural numbers have characteristic 0, basically. Okay, these are univariate polynomials, and these are the ones that you are used in classical complexity theory with the complexity classes P, FP, and P space. Now we also have talked about parameterized complexity in the discrete setting, where we measure the computational cost in terms of two parameters. One parameter n as here, the binary length of the input, for example, polynomial in the binary length of an input, but there's also another parameter, which we often call k, such as the tree width or the size of a vertex cover. That's what we covered in fixed parameter complexity and parameterized complexity. And here the resource points are bivariate polynomials, right? So polynomials that may depend on n and may depend on k, two variables, right? So, and bivariate polynomials, one way of introducing formally is to say this is a smaller set of terms that again use the same constants and now two variables n and k, the secondary complexity parameter, and these induce bivariate functions. Bivariate polynomials induce bivariate functions when we interpret both the variables n and k as natural numbers. Then the result will be another natural number. So this is a polynomial interpreted or identified with a bivariate mapping in two variables. And the red one here is the newly introduced secondary complexity parameter k. Okay, bivariate polynomials. But as you recall, when we talk about computing functionals, we also have two parameters. One is the binary length of the integer argument, but then there's another uh, 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 complex cost parameter, which is not the binary length, not a fixed number, but actually a function from natural numbers to natural numbers. And we cannot plug them into these kind of polynomials because they expect natural numbers as as assignments to the variables, not natural number functions. So this is good for fixed parameter complexity, for parameterized complexity, bivariate polynomials. But when we talk about higher type computation, we need to also consider higher type polynomial resource bounds, specifically something which has been known as second order polynomials. Second order polynomials have two, are also composed for using two variables, like here, one variable n, which is interpreted later as a natural number, and another secondary or second order variable, which here we call lambda, which will be interpreted as a function from natural numbers to natural numbers to reflect that this is a higher type polynomial. So formal definition is again, the second order polynomial ring in these two variables is the smallest set of terms that contain the constant 0 and 1 as previously, but in addition contains variables n, the same variable as previously, uh, replacement for or placeholder for a natural number, and lambda, uh, placeholder for function from natural numbers to natural numbers. And of course, now we need to observe some syntactic restrictions. But first of all, also here, we take the closure of these atomic terms under addition and multiplication, and we'll discuss closure under composition on the next slide. So please be patient about that. For now, um, let me point out that now if we assign the variable n as a natural number and the second order variable lambda as a function from natural numbers to natural numbers, then this polynomial gives rise to a higher type function, so functional, which receives integer as argument and integer function as argument and produces an integer as value. And this is exactly what we need to measure and to define computational complexity of such functionals. So in the classical univariate and bivariate setting, we also have the notion of a degree of the polynomial, right? So for example, the degree of a, but first, let us first consider an example of a second order polynomial. So here you see an example of a second order polynomial. So here, for example, is one term using the variable n cubed. That is means we use the closure under multiplication of the variable with itself, and also closure under multiplication with the second order variable lambda applied to the first order variable n. It makes sense. And here's another more interesting term. So this term again is a product closed under multiplication of the natural number variable n together with a second order variable lambda. But now the argument to lambda is itself a term, which makes sense because we now also want to maintain closure under composition. So here we have to impose that. Here it's not a consequence. Here it's an axiom, closure under composition, namely the argument to the second order variable lambda is in terms second order polynomial, which also involves lambda and n, like here. So let's have a closer look at this argument to the second order variable lambda, which is again here the sum of two terms. And the second term is now product of the natural number variable with the second order variable lambda cubed applied to the natural number argument n. And the other term is here, where we also have some variable cubed product with a second order variable lambda applied to now some complicated term. And this is just one example. As you can imagine, you can iterate this lambda further and further by using the required or the promised closure under composition, which in the second order is now not a consequence, but an axiom. And now we want to talk about the degree of these various kinds of polynomials. And again, we're going to start talking about the degree of univariate polynomial. So here you see the definition, an inductive definition, since we've defined univariate polynomials by structural induction as the least set of terms that contain 0 and 1 and the variable n. So we're going to also analogously define the degree of these polynomials by structural induction. The degree of the constant 0 is defined to be minus infinity. The degree of the constant 1 is defined to be 0. And the degree of the variable n is defined to be 1. And so the degree is now going to be a function from univariate natural number polynomials to the natural numbers, including minus infinity. And the minus infinity is used for a reason that will become apparent in a minute. But now we need to make the induction step in our structure induction, define what is the degree of the sum of two polynomials and what is the degree of the product of two polynomials, because that's how the general polynomial, univariate polynomial, is defined, by taking the closure under these two operations of these atomic expressions. And the degree of the sum is simply defined to be the maximum of the degrees of the individual components of the sum, and the degree as a product is defined to be the sum of the degrees. And I leave it to you to verify that this formal definition of the degree of a univariate polynomial coincides with your intuitive notion that you have in the back of your mind. Okay. Now let's move on to bivariate polynomials. No, let's first record an interesting corollary. Namely, we know that these polynomials are closed under composition. What about the degree of the composition? Then turns out that the degree of the composition is the product of the degrees. So in a sense, the degree behaves maybe a little bit similar like a derivative or like a logarithm. So addition becomes maximum, product becomes addition, and composition becomes product of the degrees. And now we move on to bivariate polynomials in two variables. And here we only need to add another definition, namely the degree of the second variable is also 1, naturally. And everything else remains the same. Degree of the sum is the maximum of the degree of the product is the sum of the degrees. And I leave it to you to prove, for example, by structural induction, that still the degree of the composition is the product of the degrees. And this induced degree is sometimes called total degree to distinguish it from the maximum degree. So here in the bivariate setting, we consider the total degree, and the only new definition or extension of the univariate definition is to define that the degree of the new introduced variable k is also 1, like the degree of the variable n. And after this preparation, we can now start talking about the degree of a second order polynomial. So the degree of a second order polynomial will not be a natural number. Oh, right, I promised to explain and justify this minus infinity here. And this is because minus infinity is the natural number of the maximum function. So if one of them, right, we can always write a polynomial as a polynomial plus 0, right? That's artificial way of writing p as p plus 0. And this means that this definition also covers in this case, namely in this case, the degree of p plus 0 is the maximum of the degree of p plus minus infinity, which is kind of cancels, right? The maximum of something with minus infinity is just something. So this makes this kind of consistent, this setting. Okay. And now, as promised, moving on to the degree of a second order polynomial. So this is our ring of second order polynomials in two variables, one integer variable and one integer function, higher type variable. And the result, the value of this degree is not just a natural number including or minus infinity, but it's a function from natural numbers to natural numbers including minus infinity. And it's defined again by structural induction as follows. So these definitions are pretty straightforward, but observe that minus infinity, 0, and 1 are here to be interpreted or understood as constant functions of one natural number argument, right? So they don't depend on anything. Things start to become interesting when we talk, right? And we also extend the to composite terms using this rule that sum of two polynomials has a degree which is equal to the maximum degree, and the product of two polynomials is equal to the sum of the degrees. Only now we need another additional definition to define this composition operator. Namely, if we have a second order polynomial, then lambda applied to this second order polynomial is again a second order polynomial. And the degree of this induction step polynomial is now m times the degree of the original polynomial, where m is the new variable that expresses the dependence on this natural number function parameter. Right? So m is a natural number here, and we apply this the degree, second order degree of the second order polynomial, which is a function of natural numbers, which we apply this function to the natural number argument m and obtain a new value. And this value is defined by structural induction to be m times the degree of the original second order polynomial. Okay. Let's consider an example, right? So we had this complicated example here. Now let's calculate the second order degree of this example. Second order degree says, let's use it. So here we have two terms with plus. So, and by structural definition, the degree of this large expression is the maximum degree of these two sub-expressions. So let's first calculate the degree of this one. The degree of this here, the degree of n to the third, is of course 3, right? Like in the classical case. But I leave it to you to verify that this is still the same here. Here the degree of n is 1, and the degree of the product is the sum of the degrees. So the degree of n squared is the degree of n times n is the degree of n plus the degree of n is 1 plus 1 is 2. And similarly, the degree of n cubed is 3. Now there's a multiplication sign, and the product of the degree of a product is the sum of the degrees. So the resulting degree will be 3 for this plus the degree of this expression. But the degree of this expression, according to this inductive definition, is m times the degree of the inner part. The degree of the inner part is just the variable n, which is 1. So it's m times 1, so it's just m. So this is the degree of this part, plus leads to the maximum, and this we expect to be the degree of this part. So let's look at it. There's this n, which leads to the 1, plus leads to n, times leads to plus, lambda leads to the variable m, and in this term, the argument is now becoming a product, right here, this definition, m times the degree of the argument to lambda. This is the argument of lambda. The argument to lambda is in terms a sum, so there's another maximum here. And here we have, let's look at this degree first. The degree of this is 1 plus 3 times m, that's here, 1 plus 3 times m. And the degree of this is 3 plus m times, and the degree of this here is 2. This part doesn't matter for the degree. This dominates the degree. So here, 3 plus m times 2. So this is the degree of this complicated expression as defined here inductively. It's the maximum of these two expressions, where the second again involves a maximum. So very complicated expression. But let's observe that for sufficiently large choices of the natural number argument m, this actually becomes much simpler when the maximum is attained by one of these terms, namely when m is at least 2, then actually this part dominates, this part dominates the degree. Notice that every subterm here is monotonically increasing. So when m is at least 2, then this part dominates over this, and therefore the maximum is given by this. And also in this case, this part becomes unimportant, is dominated by this. So for m at least 2, the degree of this here is this expression, which I'd like to point out is again a polynomial, a classical, a univariate polynomial in one variable m. So let me say that again. In this example, here this example is the second order polynomial. We've just defined second order degree of second order polynomials by a complicated structural induction. We have calculated the second order degree of this complicated second order polynomial, which is again complicated, but for all sufficiently large m, this is just an ordinary polynomial. It's not in expanded form, but still a polynomial in one variable m. Okay, and we will see in this slide that this is no coincidence, but that this is true generally. And let's, before that, calculate some values of this degree for various arguments m. Let me say it again, the degree of a second order polynomial is not a natural number, but a function of one natural number. And this natural number argument is what we here abbreviate with the variable m. And so when m is equal to 0, then this expression here becomes 3, and this here becomes 0. So the maximum of 3 and 1 is of course 3. So when m is equal, that should be an m is equal to 0, then the degree evaluates to 3. When m is equal to 1, it evaluates to 6, and so on. I'll leave it to you to verify that. And starting with m equal 2, this coincides with this polynomial. For lower values of m, it is not a simple polynomial, but a different complicated expression. And as I said, this is no coincidence in this example, but this is generally true. Maybe we have the following theorem. If we fix a second order polynomial p in two variables n, first order variable and second order variable lambda, then for every natural number d, when we plug in this particular second order value for the second order function lambda, then we obtain a first order polynomial. Let me say that again. Remember that when we interpret the variable n as a natural number and the variable lambda as a natural number function, then we obtain the second order polynomial relates to a natural number. And this is what we do here. We just take a particular example, a particular case of a natural number function lambda, namely the one that takes n to the d, using here some kind of implicit lambda notation, where d is here fixed. Okay, so and if we do that, then the statement says the result, in this case, the second order polynomial boils down to a first order polynomial. And again, let's verify that. If we replace lambda here with, let's say, a quadratic polynomial, so the case d equals 2, quadratic polynomial, then this here means n to the third times n squared, which is n to the fifth. And similar here, if lambda is square, the argument, then this becomes n to the sixth. And with this, that's m to the 7. And here this becomes n to the fourth plus 2 times n to the third plus n squared. And so with this, and then there's another squaring operation. So again, yeah, you can please confirm that with manual calculation, that if we replace lambda, the generic function here, with a particular function that takes n to the d, for d fixed d, then the second order polynomial boils down to be a first order polynomial, an ordinary polynomial. That's the first statement of the theorem. The second statement of the theorem says that actually the degree of the second order polynomial, if we plug in right? It's some function from natural numbers to natural numbers. And if we plug in for the argument the degree of some first order polynomial p. Okay, so p is a first order polynomial, capital D is a p is a second order polynomial. We take the degree, which is a function from natural numbers to this set, and we plug into this function this particular natural number, namely the degree of the first order polynomial small p, then the result will be a natural number or minus infinity. The statement says this coincides with the first order degree of the first order polynomials where we fix the second order parameter to be the polynomial p. So this is now a polynomial here in one variable, n entering here, but n entering also here implicitly here. So and we know what the degree of this first order polynomial is. It is a first order polynomial, and this coincides with this. Put differently, the degree of this resulting first order polynomial depends only on the degree of this ordinary polynomial as second order argument, not on anything else, not on the other parts of the structure of this polynomial. And of course, depends on the second order degree, which we have defined here. It's a second statement of the theorem about the properties of the second order degree. Third order statement says, for all sufficiently large d, if we plug in d here, then the result will be indeed a first order polynomial. So this kind of generalizes our observation here. Here the statement was whenever the degree is at least, whenever the argument is at least 2, then this complicated expression becomes an ordinary polynomial. And the statement here says this is true in general for all sufficiently large arguments. The second order, the degree of a second order polynomial is a first order polynomial, but only for all sufficiently large. And finally, we want to talk about counterpart to this composition degree property. But first, we need to talk a little bit about what the composition of second order polynomials, because there are two ways of composing second order polynomials. Here, there's only one way. Take this polynomial and kind of plug it in as a variable in this polynomial. But here we have two variables, right? And the two way of composition is whether they plug in the second order polynomial q in the first or in the second place, as the first or as the second argument. Let's first discuss the latter, which makes sense naturally because the second parameter, the second variable, must be a function from natural numbers to natural numbers. And this is this, right? As long as we fix second order argument lambda for this polynomial and take its dependence only on the first argument, m here, then this is indeed a function from natural numbers to natural numbers. Right? You see that here. This is a natural number, and it returns this value of the second order polynomial on this first order argument and the tentatively fixed second order argument lambda here, and returns a natural number. So this is indeed a natural number. This is a function from natural numbers to natural numbers. That's one thing. And this is our notion of composition. Okay, so plug in this particular kind of second order variable here and keep its dependence on the first order variable n and on the second order variable here, which is now does not enter directly, but after the composition, that's the point of a composition. The other composition is when we plug in the second order polynomial for the first variable. And that doesn't really immediately make sense because the first variable, as you recall, must be a natural number, not a second order polynomial. So here, this is an abbreviation for take this polynomial at the given natural number argument and at the given second order function argument here. Then for fixed n and lambda, this is a natural number, and we can plug this in. So now the second order function lambda here enters into this composition in two places, here and here, simultaneously. So to summarize, in second order polynomials, we have to consider two ways of composition. And now we can state how the degree gets affected with both different kinds of composition. So the second kind of composition, the simple one where we simply plug in the polynomial for the natural number variable, that kind of corresponds to this case where we plug in the polynomial q for the integer variable in p. And indeed, then this kind of composition results in degree being the product of the original degrees. So that's our counterpart to this. But, the interesting thing, the other kind of composition when we plug in the second order polynomial argument in the second position, then the degree actually becomes not the product of the original degrees, but the composition of the degrees, which is kind of surprising, but let me remind you that the second order degrees are first order polynomials, and we know that and what it means to compose first order polynomials, and this is exactly what is meant here. So this kind of composition results in the product of the original degrees as first order polynomial, and this kind of composition results in the composition of the degrees considered as first order polynomial. Okay, so these are properties of second order degree, and yeah, that wraps up our consideration of polynomial bounds for high type computation, namely second order polynomials, which take into account kind of the size of the oracle, which is a function, and therefore its size is not just a natural number, but it's a function from natural numbers to natural numbers. That's all for today. Thanks for your attention and goodbye.